Okay, can you guys hear me out there? Okay, hopefully you're able to see the molecule of the lecture that's displayed now. We'll get started in about 10 or 15 seconds. Okay, so we'll go ahead and get started. So we'll kick off with this molecule of the lecture, and we'll do some questions on that, and then we'll get back into our discussion of mass spectrometry. So I don't have a QR code for this one because it's not, to my knowledge, a commercially prescribed prescription drug. But the molecule's name is discodermalide. And so if you look at this name here, it has this plus in front of it. And later on this semester, we will learn what that plus sign means. But this is the structure of discodermalide here in the bond line convention. Below it is the space filling representation, and then over to the right of that is the ball and stick. So as you can see, the molecule sort of adopts sort of like a snake or linear topology, I guess. So discodermalide is a polypropionate marine natural product. So what does marine natural product mean? Can you? So let me switch my camera there. Okay, so what is a marine natural product? Basically, these are naturally occurring molecules that are isolated in this example from either a sea sponge or some marine organism. So I know a lot of you are biology majors, and so if you're interested in going into graduate school, say in marine science or oceanography, this molecule was actually isolated by this scientist here, who worked at Harbor Branch, and basically what these scientists do is, see, they do scuba diving missions, and they look for these sponges or sea squirts or whatever they are, and they harvest them, they bring them back to the lab, and then they will extract them and do what's called bioassay guided fractionation. So basically what they're doing is it's an extraction of this molecule with a solvent, so chloroform or methanol, and then they're taking those extracts and testing them against, say, cancer lines. So this molecule was found to stabilize microtubule formation against colon, breast, and ovarian cancers. And Novartis subsequently took this molecule and made it synthetically in the lab. It's interesting. I think the route to make this in the lab was over 30 chemical steps, so that's quite long. But the benefit of this molecule is it is active at I believe, nanogram levels. So as I showed you before, when we were talking about a molecule of the lecture, I think Lipitor had the dose was like 40 milligrams. So something like this you could get away with dosing in like microgram amounts. So even though it is complex, you don't need as much of it. So let's get to some questions about discodermalide here. So the first one, what functional groups are present in discodermalide? So in the chat box, type a letter. You know, when you're looking at this molecule, what functional groups do you see present? So yeah, again, the questions that you see presented in these slides, these are questions that I make, and they would most mimic what you would see on an exam if we were meeting face to face. So I sort of designed them such that, you know, there are some distractors in each possible answer choice. The best answer is B, alcohol, alkene, ester. So you have an alcohol here, alcohol. Alkenes, there's a couple different alkenes, one there, there, and there. And the ester is basically here. It's a cyclic ester. So you have a carbonyl, an oxygen, and then a carbon. So that's the ester. A, C, and D are distractor choices. There's no bromide, there's no halogens in the molecule. So A and D are out. C is also out because there's no alkyne, and an alkyne, remember, is a carbon-carbon triple bond. So discodermalide has the molecular formula of C33H55NO8. How many degrees of unsaturation are present in discodermalide? So Tenley is asking about oxygen, double bond, and nitrogen. So there are some less common functional groups that we'll encounter in the semester. So discodermalide has a carbamate. A carbamate is not an ester. Basically, I'll go back after we answer this question and show you what a carbamate is. So this question is asking about degrees of unsaturation as calculated from a molecular formula. So we have everyone's favorite Scientologist, John Travolta. He was in a famous disco movie. So there's the connection there. So the answer is, I believe D is the best answer, 7. So let's go through that. I'll flip off to the doc cam. So again, when we're considering degrees of unsaturation given a molecular formula, we always revert to CnH2n plus 2 because that is the saturated, fully saturated alkane. So I have to get used to using this .cam. So we have N equals 33. So if this were fully saturated, it would be what? 2 times 33 is 66 plus 2 is 68. So we have C33, H55NO8. Remember that nitrogen subtracts from the hydrogen count. So we actually end up with H54. The oxygen neither adds nor subtracts. So if we sort of do this simple subtraction, those cancel out. We get H 68 minus 54 is H14. A degree of unsaturation is defined as a molecule of H2. So 14 divided by 2, and that gets us 7, which is choice D. And again, what we're attempting to do in this activity with the degrees of unsaturation is develop chemical intuition from the point of view of how should we think about solving a problem. So even though we're given very simple data or information, what can we extract from that to solve a problem and ultimately increase our problem solving and thinking skills? So this part of the molecule, discodermalide, notice there's a carbonyl, a CO pi bond, then bonded to oxygen, and then bound to nitrogen. That is called, so this is sort of like an amide part right here, and over here is like an ester. But since there's both, that's called a carbamate. So that's its own functional group. So here's a very general question relating to functional groups. Which of the following correctly matches the functional group name with the degrees of unsaturation present in that functional group? So think about the basic connectivity of each of those, an amide, an alcohol, a ketone. Do they have a degree of unsaturation or not? If they do, how many degrees do they have? So yeah, the correct answer should be C. And again, what are we doing here? When you see this collection of letters to make this word amide, in your mind you should visualize something like this. So I'm going to draw just the basic parts of that functional group that we need. We have a CO pi bond bonded to nitrogen. So that's sort of the basic things you need for an amide. So I could put in like a ball, and like those would be things bonded to those elements. They could be anything basically, but what is drawn there, that's the basic stuff you need for an amide. And so the pi bond there is 1 degree of unsaturation. So what about an alcohol? You basically need these elements, OH, and then something bonded to the oxygen. So that has no degrees of unsaturation. And the ketone is basically carbon doubly bound to oxygen, and then 2 other carbon-based groups. So that's 1 degree of unsaturation for the pi bond. So let's do another one of those. Now we have an acid, an alkyne, and an ester. How many degrees of unsaturation are present in those functional groups? So carboxylic acid, an alkyne, and an ester. What do you think the best response is for this? Yeah, so this one's going to be A. A carboxylic acid has 1 degree of unsaturation, an alkyne has 2 degrees of unsaturation, and an ester has 1 degree of unsaturation. So again, we're developing a chemical intuition to think about like this word, what the structure looks like, and what a degree of unsaturation is. And I hope that you'll see we are going somewhere with this as we learn more about interpretation of data, so mass spec, IR, and NMR. You'll see how we can think about solving the structure of an unknown compound. Any questions before we move on, picking back up with the mass spec data? You can type it in the chat or unmute yourself. Okay, so let's recall what we did last time. We were given this slide with a mass spectrum. We had a parent mass M over Z equal to 58. So here's the parent mass, M over Z at 58. We were asked to determine the molecular formula from that and draw out some possible isomers. So I see in the chat, how is it A? So let me just finish up with this question here. So an acid. So what you need for an acid, you need that collection of elements bonded together. So over here can be anything, basically carbon. So that's 1 degree of unsaturation. An alkyne, you have a carbon-carbon triple bond. You have anything bonded there or there. So now you have 2 degrees of unsaturation. For an ester, you have carbon-oxygen pi bond, oxygen, and then something here that's not hydrogen, and then something here as well. So that's 1 degree of unsaturation. So again, the difference between an acid and an ester, an acid has this H, an ester has carbon there. So returning to this mass spectrum, again, the x-axis is mass over charge. Z is typically 1, so really what you're looking at is the mass. The highest number mass you see, that's the parent. That corresponds to the intact molecular formula. The peak you see at 100% abundance, that's called the base peak, and that's the fragment, or that's the ion that's produced most often in the mass spectrometer. So when we did this, we found basically for M over Z equals 58, we found a molecular formula of C4H10. Then we proposed basically butane or 2-methylpropane as the isomers. So what about, let's do some different types of these. So the next one Now we have a parent mass of 46. That's what we see here. That's the highest mass, 46. And now it's telling you the molecular formula contains oxygen. So there's one oxygen. Determine the carbon and hydrogen count. So it's basically asking you, what is the molecular formula if you're given M to Z of 46? Once you do that, propose as many reasonable constitutional isomers as you can. How can you use carbon and hydrogen uniqueness to differentiate them? And then can you figure out what the structure of the M to Z31 ion is here? So if you take 46 minus 31, that's the fragment you lose to produce this signal at 31. So let's take some time, do some drawing on your paper and see if you can come up with the molecular formula that belongs to a mass of M to Z equals 46. So M to Z equals 46 has one oxygen. The remainder are carbon and hydrogen. So we got some early responses by Jalen and Hannah. Let's just take another minute or two. See if people come up with that or something else before we go through the logic of solving this. So this might sound a bit strange, but so I'm looking at this dot cam. Hopefully you all can see this red pen. Can you still see the red pen now? Okay, so the window that I'm looking at, there's part of it that's like a shadow, and so I just want to make sure that you can see everything I'm writing down. So Aiden, that's not viable because there's only one oxygen. That's part of the clue. So let's go through this. You're told from the start there's only one oxygen. So M to Z equals 46. That's your parent. What does that mean? That contains all C, H, and O. You're told there's one oxygen atom. So let's take 46 minus, how much is oxygen worth? What number should I write here? Tenley says 16. So again, yeah, that's the atomic mass of oxygen. So that gets us 30. There's only one oxygen. So what does this 30 correspond to? The remaining C plus H. So how do we find the maximum number of carbons in 30? What should we do next? So Ian says 30 divided by 12. That's essentially going to get us 2, right? So we always really want to work with whole numbers here, even if you have something repeating. And it's sort of as best practice just to go to like the lowest number. So this is going to be 2 and something, so we're just going to go with 2. So that's the max number of carbon. So 12 times 2 is 24. So 30 minus 24 is equal to 6. That's the max number of H. So what have we done? We've come up with a potential molecular formula, C2H6O. And you may or may not be used to thinking this way. I know a lot of students, they want the answer, they want to know exactly how to get to it, and they want to be right 100% of the time. So I think this class, organic chemistry, will show you that you really have to be versatile in how you think. And right now, this is a claim. So if we were lawyers, we are claiming this as a possible answer. And what we're going to do subsequently using different pieces of data is back up that claim. So if this is what we're proposing, how many degrees of unsaturation are present in that molecular formula? So Kenneth, Charles, Ian, Aislinn, Aiden all say 0. And that's right, because N is equal to 2, and we go through Cn, H2n plus 2. Oxygen neither adds nor subtracts, so basically we get C2H6, and we subtract that from what we're given, that gets a 0. And why is that helpful? Because if we say there are 0 degrees of unsaturation, there are no rings and no pi bonds present. So anything you draw in terms of your possible structures, you cannot put either of those things in those structures. So given this molecular formula, C2H6O, why don't you draw some possible constitutional isomers? So you can either write names in the chat or show your video and show your structures. However you want to do it. So take a couple minutes, propose some structures. There are some responses in the chat. Again, I strongly encourage you to try to figure this stuff out on your own as well, so you know how we're thinking about this stuff. Anyone want to show their structures on their camera? Sarah, that looks good. Thank you. Ian, those are correct. Anna has an interesting way of representing dimethyl ether in the chat there. Carly, those are correct. So I'll write those structures on the paper here, but what we can consider now is, you know, of those two constitutional isomers, how would you differentiate them according to carbon-hydrogen uniqueness? So we have ethanol and we have dimethyl ether. How many unique carbons does ethanol have? So I see a lot of twos. So yeah, so there's one, two unique carbons. How many unique sets of hydrogens does ethanol have? So hydrogens now. Getting some threes. So we have 1, 2, 3. And what is the ratio of all those sets? The ratios. How many of each type are there? So Columbia and Ian say 3, 2, 1. So 3, 2, 1. So again, that total is your 6. Remember from back here, 6. What about for dimethyl ether? How many unique carbons are there? Yeah, there's only one, right? Because the molecule is symmetric. There's one unique carbon. How many unique types of hydrogen? That's 1 as well. So since there's only 1, there's 3 and 3, and that gets you 6. So again, with this uniqueness exercise, that's the conceptualization of NMR spectroscopy, both carbon and hydrogen. So let me ask you another question related really back to chapters 1 and 2. You have ethanol and dimethyl ether. Without looking up the physical properties, which one of these compounds would you expect has the higher boiling point? So we see a lot of responses for ethanol has the higher boiling point. So Ian answered the next question because it can hydrogen bond. So let me just flip the page here so we can see what that means. So if you have two molecules, again, if you have like a liter of ethanol, obviously you have more than 2 molecules in there, right? But this is just demonstrating the attractive forces. So a lone pair from one oxygen is attracted to the hydrogen from the other hydroxyl group, right? So this is called a hydrogen bond. And it's an attractive force. So, you know, think about you have millions, trillions of these ethanol molecules, and they're attracted to one another. So if you're boiling something, you're taking it from the liquid to the gas phase, and you have to put heat into that to break these interactions and boil the molecules away from one another. So the more of those type of interactions you have, the higher the boiling point. Dimethyl ether does not have that. So again, hydrogen bonding, you have to have like an OH or an NH basically. These molecules don't have that, so this is going to have a much lower boiling point because there's only really, say, dipole-dipole attractions or induced dipole-dipole or basically polarizability attractive forces. So this will have a much lower boiling point. So let's consider the well, before we move on, any questions about any of those type of thought processes that we just went through? So is this due to the strength of the H bonds? Yeah, so we'll get into bond strength probably a little bit later on in the semester, but yeah, this even though, so I'm drawing it sort of as like a dashed line, right? We know that this bond here, we consider that line a true covalent bond, and that's really strong. So a dashed bond, it's a much weaker interaction, but yes, it has some strength to it, and that's what you have to put heat into the system to overcome, is that attractive force. So again, what we're aiming to do is part of our learning outcomes for this course is really develop an intuition about thinking and solving problems. Again, I know most of you are not going to be organic chemists in life, but whoever you end up working for in the future and you're earning a paycheck to pay your bills, they are going to ask you to solve problems, and you want to have a very good problem-solving skill set. And I hope that this course really shows you different ways of thinking about things. So let's get to this last prompt here on this slide. Can you figure out the structure of what is the M over Z 31 fragment? So what structure belongs to this fragment? So you're given a hint here. So you have parent M over Z equals 46. You have, I'm going to say ion, M to Z equals 31. So if you subtract that, you get 15 as a fragment lost. So Jalen is asking, is it a methyl group? So it is a methyl group. So let's understand how did we convert this number into how do we think about converting this number into this word or this representation of methyl? So we're going to use the same sort of math, right? So if we take 15 as the fragment and we divide that by 12, that's getting us the maximum number of carbons, so 1 carbon atom. So all we did was take this number. This is the atomic mass of carbon. It's going to be 1 in something, but again, we go to the lowest integer. And then we take, so 15 minus 12, because that's the carbon contribution to that mass. That gets 3, and this would be the H atom contribution. So we get CH3. So the parent ion is losing a mass of 15 and it's producing this ion 31. So if you look at your two proposed constitutional isomers, and you think about how could each of those lose a methyl group. And so what is basically happening in the mass spectrometer is that obviously these both have a mass m to z of 46. And what does this z mean? So I'm going to write this as just plus, because that is how you see those numbers. That 46, it's an ion. This 15 that you don't see, I'm calling it a fragment. And fragments are neutral, so you're not seeing that sort of lost. So how do you lose minus CH3 from here? So it would be like clipping this bond. I'm just going to write minus 15. So what you would end up with here is so we lost this methyl group, right? We don't see that it's lost as 15. What we do see, this is M to Z of 31. So we have C. So we have one carbon, 1, 2, 3 hydrogens, and one oxygen. So if we do the math, that should get us to 31. So what about if we lose CH3 here? You can't see that. Again, I'm sorry about this doc cam. I have to move the page. So let me just go through that. This is your parent. You're losing 15, so you're losing that methyl group. Again, this is neutral. So that's the mass you lose. This is the structure that you see at 31. CH3O. So what about the dimethyl ether? If you were to lose 15 from here, it's one of these methyl groups. So you're breaking that bond, you're losing a methyl group. So what do you end up with here? Oxygen, CH3 plus, so that's what you see as 31, M to Z of 31. So again, that's CH3O. So again, 12 plus 16 is 28 plus 3, that gets you 31. So any questions on this slide before we move on to the next slide that contains nitrogen? So I would concur with what Mac, Aiden, Ian are saying. It's most likely dimethyl ether because this one you have a chance to lose 2 methyl groups, which would give you a very strong natural abundance at 31, whereas this one can only really lose 1 methyl group. So mass spectrometry is a field unto itself, and like I said in the prior chat session, these spectra all have certain fingerprints, and that's what's used in like a lot of toxicology experiments to determine the identification of unknown substances. So Aiden, is it possible to determine which one it is? Yes, I believe it's the dimethyl ether. We could go to the NIST website and look up both dimethyl ether and ethanol and see if their signatures are different. But I think this one is the dimethyl ether. So let's now consider a molecular formula that contains one nitrogen. So we're doing the same sort of exercise, but the molecular formula has one nitrogen. The parent mass is 45. We're going to go through the same exercise, but now look at this nitrogen rule here. A molecule with an odd nominal mass has an odd number of nitrogens. 1 is an odd number, so 45 has 1 nitrogen. So let's go through the same process and propose some constitutional isomers for a molecular formula of 45. So again, can you guys see this word that I'm pointing to now with my pen? Okay. So I just want to make sure that this whole sheet is in the .cam viewing area. So this mass is odd. So that tells you there is an odd number of nitrogen atoms, and specifically I'm telling you it's 1. So Carly, I'm not sure how to fix the viewing issue that you have. So what do you think a good molecular formula is? So we have some fast responders here. C2H7N. Again, that's our claim. So let's use some logic. So Hannah, you might have an issue with degrees of unsaturation. So Hannah, use the formula for degrees of unsaturation and try to figure out why that proposed molecular formula cannot be possible. So if we have given m to z of the parent equals 45, we have 1 nitrogen atom. How much is nitrogen worth, atomic mass wise? So 14. So that gets us 31. Must contain C plus H. We go through the same exercise. 31 divided by 12. That gets us 2 as the max number of carbon. So 31 minus 24, so 12. 12 times 2 is 24. That gets us 7 as the max number of H. So our proposed molecular formula, C2H7N. So Mac has some proposed isomers up there already, and so before we draw those out, how many degrees of unsaturation are present in this molecular formula? So again, there's 0. So again, this molecular formula has to become, because there's a nitrogen, it has to subtract 1 hydrogen. So C2H6, so N is equal to 2. So it should be CnH2n plus 2. So if we put that in there, we get C2H6. Because they're the same, we get 0 degrees of unsaturation. So Alexis, that is correct. 12 is from the atomic mass of carbon, and the 24 is 12 times 2. So that's the number of these carbons. Yes, that's correct. So 0 degrees of unsaturation, and Mac has proposed so ethylamine and dimethylamine. So Tenley is asking, why did I use C2H6? So this is what we found right here. This is what we found. Nitrogens have to subtract a hydrogen. So we have 1 nitrogen, the 7 becomes a 6. So this is what we use in finding degrees of unsaturation. So that ties back into why when a molecule has an odd number of nitrogens, why the mass is odd. So as you start picking up on these things, you'll see that H7, this is one of the first molecules we proposed with an odd number of hydrogens as well. So what kind of amine is this? If you had to classify this amine and this amine, remember classifications of amines? How would you classify ethylamine? So this is primary. Again, we're looking at the nitrogen and we're just counting the bonds to carbon. We have 1. So the dimethylamine is therefore secondary. So between ethylamine and dimethylamine, which one do you think will have the higher boiling point? Notice now they both have hydrogen bond donors and acceptors. So which one will have the highest boiling point? So yeah, just using some simple logic, it should be the ethylamine, because this has twice as many NH bonds than the dimethylamine. So I want to sort of move on to the next couple slides in this slide deck. Any questions before we move on? Because I want to get to the halogen atoms. So here's this slide where we talked about isotopic abundances, or isotopic mass in their natural abundances in mass spec. So mass spectrometry is really useful for determining the presence of halogens, particularly chlorine, bromine, and iodine. Fluorine, not really so much, and the reasons for that are the following. So here's fluorine. Fluorine 19, it has the mass of 18.998403. So that isotope is 100% abundant. So compare that to chlorine, which has two isotopes, 35 and 37. So those are the masses, and they occur in the ratio of 75-25, basically, so 3 to 1. Bromine has two isotopes that occur in a 1-to-1 ratio, 79 and 81. Iodine has a single isotope that's 100% abundant, but it's different from fluorine in that if a molecule contains iodine, you will typically see that fragment 127 in the mass spectrum. So I want to visually show you that so you can see how these numbers look in data form. So we're going to consider basically a monosubstituted benzene ring. So all of these next four examples, you're going to see this the common thing is the benzene ring, and what changes is the halogen. So this is fluorobenzene. So here we are. Fluorine does not have a distinct signature in the parent region. So we said fluorine as a single isotope, it's 100% abundant. So the exact mass of this is 96. So there's really nothing that tells us there's fluorine there. So in the next slide, we're going to look at chlorine. So watch how the parent region changes for chlorobenzene. So chlorine has a doublet-like peak of the parent with a ratio of 3 to 1 that corresponds to chlorine 37 to chlorine 35 to chlorine 37 isotopes. So look at the exact mass of the parent. The parent at 112 contains the 35 isotope. The parent at 114, so look at the difference between this. 36.9 minus 34.9, that's 2. So this parent here contains the 35 isotope. This parent here contains the 37 isotope. So when you see a parent of this 3 to 1 ratio, so you can sort of eyeball, that's 3 to 1 ratio. That tells you this molecule most likely has chlorine in it. So does everyone sort of see that? The chlorine 35 to 37, the natural abundance is about a 3 to 1 ratio. So what you're seeing, this mass has a chlorine 35, and then this mass has a chlorine 37. So in the next slide, we're going to look at bromobenzene, and you're going to see the parent masses now are about a 1 to 1 ratio. So see here 156, 158. That corresponds to C6H5 bromine. So the 156 mass has the bromine 79. The 158 mass has the bromine 81. So see how this signature looks different? It's like 1 to 1. Again, here's chlorine 3 to 1. Now iodine, even though it's 100% abundant, look at this number here, 127. So you'll typically see a small peak at 127, and that corresponds to the iodine ion. So C6H5I has the parent mass of 204. If you ionize this bond in the mass spectrometer, you see the 127 as the iodine. 204 minus 77, that gets you 127. So from this parent to this fragment is losing the iodine atom, in basically 77 corresponds to C6H5. So any questions on that before I'll show you some more sort of mass spec data before we wrap up today. So what I will do is I will upload some worksheets as we learn more about IR and NMR, where basically you're given mass spec IR NMR data, and you have to figure out what is the molecular formula and what could the possible structures be. So it's really like detective work. So here's some mass spec data. You're given this molecular formula C8H7OCl. And so look at the parent. See this parent region? How it sort of resembles 1-to-1, or excuse me, 3-to-1. This next example, even though it's pretty tiny, it says the parent ion 148 to 150. It's super tiny, but it's a 1-to-1 ratio. Then the last one, you're not given a molecular formula, but it says contains a halogen, and you see a peak at 127. So that 127 is indicative of iodine being in the molecule. So that's probably going to wrap up our discussions of mass spec. I'm going to post some screencasts on mass spec and IR over the weekend that you should watch. I'll post some of these problem solving worksheets as well, so you can start thinking about those. Your homework 14, 15, Orion 14 and 15 are now open, so try to start doing some of those problems relating to the mass spec at least. Any questions before we wrap up for today?